So here we're going to be studying water in the atmosphere. We cannot see water vapor, but we feel it as humidity, the liquid form of water. It's so familiar to us that we just call it water. The solid form of water that we usually call ice is just common everywhere today, including places where it's never even cold enough to freeze it naturally. No matter what phase it's in, a water molecule is the same, an oxygen with two hydrogen atoms attached, therefore H2O. Their energy, as exhibited by their speeds of movement, is the only thing that makes them act differently in water's different phases. So conservation of energy plays out here. In one of the very basic laws of nature, it says that energy cannot be created or destroyed, but it can change form. When a water molecule slows down enough to change from a vapor to a liquid, or even ice, the kinetic energy of their movement changes into another form of energy, heat. When water evaporates from a pond to become water vapor, heat energy becomes the kinetic energy of the added motion. To see how this works, imagine being outdoors on a hot day. To make this thought experiment work even better, imagine that the humidity is low. As you exercise, you begin to sweat. But the sweat quickly disappears. What is happening? The sweat, which is water, is evaporating into water vapor in the air. Your body's heat is supplying the energy needed to speed up the molecular motion. Increasing molecular motion in the sweat to turn it into water vapor. This heat is latent heat, and the evaporated water is carrying it away from your body, cooling you off. So if we look here at latent heat, how we can go from ice to water to vapor, so a solid to liquid to a gas. On the top half of the graph, we have where heat is being absorbed into a substance. So if I have ice and it's absorbing heat, it's melting. In the process of melting into a liquid, it absorbs 80 calories. Typically that's 80 calories per gram here. And then the water would take then another 540 to 600 calories. We'll go with 600 calories here to evaporate. It takes more heat to take liquid water to its latent heat of vaporization, or the heat of vaporization. And if we were to go just directly from ice to water vapor, this is called sublimation. It's a phase change from a solid to a gas. And this is why ice cubes in an ice tray, if you still have those, if you even know what those are, actually get smaller over time. But this is the process of sublimation, and they absorb 680 calories of heat. But when I go from a vapor to a liquid to a gas, we're actually releasing heat energy. So in order to get water vapor to a liquid, it must condense. Therefore, it must release 600 calories. And then once it's in a liquid form, in order to freeze, it must release another 80 more calories to go into the solid form. And the process of going from water vapor to that of a solid ice form is called deposition. This releases 680 calories. So you notice if we skip both steps in either the sublimation, going from a solid to a vapor, or a gas to a solid, it takes the total 680 calories to change that phase. It's a one-step process. Deposition is the reason why you have to scrape your windows in the winter. When it's freezing, right, the water vapor in the atmosphere freezes to your windows. It goes from a vapor to a solid, and we see that in terms of having to scrape our windshields. So our lab that we did was heating water and phase changes. We're really looking at latent heat. Number one, part one. It doesn't matter if you look over here or over here. These are really the same thing. Here we have located part one. The ice rises in temperature from -10 to 0 degrees. The ice is gaining heat, but has not yet melted. Number two, the ice melts at 0 degrees C. In this case here, this is called the heat of fusion. The temperature is not changing. It stays at melting point of 0 degrees C. During this time, heat energy is being used to overcome the molecular attraction of one another. This destroys the three-dimensional crystal structure of the ice itself. This, right here, stage 2 and stage 4, you'll see, is latent heat. Number three. So then the liquid water has to rise in temperature from 0 to 100 degrees. The liquid has not yet boiled. It has to rise to get to boiling point, and that's what we see here. So it takes a while. 4. The liquid then boils. This is the form of heat of vaporization. This will be step 4. This again is the latent heat, the heat of vaporization. As you add heat, the temperature is not changing. It remains at 100 degrees C. Energy is being used to overcome the molecular attraction, right, from the liquid form moving them from close together to far apart. This is your heat of vaporization. You go from a liquid form where they're close together to breaking them apart. I'm adding heat, but it's not heating up. Instead, you're breaking the molecular attractions. And lastly, the steam then rises in temperature from 100 to about 120 degrees C. The temperature of vapor increases due to having a continued heat source. So if I look at this picture over here, phase 1 is a temperature change. Location 2 here, notice I'm using these 1s, 2s, 3s, 4s, and 5s together. 2 over here is 2 over here. It's a phase change. This is your latent heat. Number 3 here, I'm heating up the water. Temperature is changing. 4 over here, it's a phase change, heat of vaporization. And here is like my number 5 here, it's a vapor. It's a temperature change. It's heating. It continues to increase in temperature. So there's the first part of a series of labs that'll help you make sense of lab exercise 8.